Welcome to our series on radome and bumper testing, where we cover everything you need to know about radome testing and the usage of the powerful QAR50. This video is about another question that concerns a lot of our customers. Radomes and bumpers are usually not flat, so how does that influence the measurement result? That's actually a very good question, but there's no good question without good answers. So here I brought one example of how a typical bumper, for example, or a typical radome could look like. So you can see there's a little bit of structure. And also, probably what you can't see very well with that part is that this part has a certain curvature in the area where the actual radar goes to. So this is the radar active area, this is the radome, this is the part that we want to measure. So inside the QAR50, I have another sample, which is part of a bumper. And also this bumper has a curvature. So the question is, how does the curvature influence the measurements that we do? So the first measurement that we wanted to do is the transmission phase. So how does the transmission phase of that specific bumper look like? And this is what we see here on the left-hand slide. So we can see that in the phase, we don't really see an effect of the curvature. And we can say, okay, this sample is quite homogeneous. And the effects that we see here are mainly caused by physical effects that can be explained. So what are these physical effects that can be explained? And this is mainly due to the focusing or defocusing of the beam if we are measuring, for example, reflection. It's the same as in optical systems. You have the convex or concave samples, and basically, depending on the curvature of the samples, you have a defocusing or a focusing of the beam, and you get different results. So first, I would like to start with the simulation results. So we have simulated the results of a single point measurement, for example, taken with a vector network analyzer or any other single point measurement device, and the results of the microwave imaging. So on the left-hand side, the single point measurement, we can see different lines. There's a blue line, which is the radome with infinite radius, so basically no curvature at all. And there's another line depicting the radome with a radius of 40 meters, which is basically the same. So you can see if we normalize on that metal plate, we still have 0 dB. And then depending on the curvature, the reflectivity differs. So if we select, for example, the 0.4 meters or the 0.2 meters, then we have a significant effect in the single point measurement. So the yellow line or the orange line, they are at about minus 8.5 or minus 12 point something dB reflectivity. So that means even though we have 0 dB reflectivity, we're not measuring 0 dB reflectivity with that certain sample due to the sheer fact that it's curved. So how does it look like in microwave imaging? So first, start with the simulation here as well. Again, the blue line and the purple line, this is zero curvature. So basically a complete flat sample as we have, for example, for the verification plates. And then again, we look at the plates with the different curvature. So 0.4 meters, again, the yellow line, 0.2 meters, the orange line. So for the yellow line with the 0.4 meter radius, we see that there's a deviation of around minus 1.8 dB. And for the orange line, we see around minus 3.4 dB. So this is the simulation result. Again, how does this look like in a measurement? So here we have prepared a sample with 0.2 meters of radius. It's metallized. And the question is, what's the reflectivity of that sample? Because in theory, we were expecting for the flat sample 0 dB, but the fact that the sample is not flat changes the reflectivity that we measure. And from the simulation, we would expect a reflectivity of round about minus 3.4 dB. So if we look at the simulation in the middle, minus 3.4 dB, QAR50 measurement result on the right, minus 3.43 dB, that is super close to what we are expecting from the simulation. So again, we have these physical effects that we can't avoid because it's sheer physics. We can't cheat the physics. But if you know what to do and if you know what you're doing, then it's basically not a too big effect. You still get a correct measurement And you have to keep in mind that with the imaging approach that we are using with the QAR50, we have this deviation of minus 3.4 dB, but measuring the same sample with the network analyzer gives us a deviation that is much higher. So just have a look back on that slide. Curvature 0.2 dB, which we are taking as a sample here, would lead to a reflectivity of round about minus 12, minus 13 dB. So that's a significant difference to the 0 dB that we are actually expecting. So again, something that you have to keep in mind when measuring the samples.